Welcome to Train Signal. I'm Ross Bagurtis, and in this video I want to talk about Ethernet and switching. Now Ethernet and switching are two really cool technologies, and Ethernet especially has been around for just an eon, and it's a really neat technology that has a pretty amazing history. So I want to tell you a little bit about the history first, and then we're going to go into look at how it actually works. Now Ethernet is probably the most popular layer 2 network protocol around right now. Pretty much every device we use as a consumer or even as an end user in a workplace uses some form of Ethernet to connect it to the rest of the world. Now we have both wired Ethernet and wireless Ethernet. And although they operate completely differently, they both have the same basic fundamental concept behind them. Now, Ethernet is really cool, actually, I think, because it was invented so long ago. As a matter of fact, Ethernet, the concept of Ethernet and its first implementation, actually predate IP addressing in its current form. IP version 4 addressing, which is what we use today, Ethernet was around for almost 10 years before that addressing scheme came out. So the way this worked was in 73, a guy by the name of Bob Metcalfe was working at Xerox PARC. At the time, it may have just been PARC, P-A-R-C, the Palo Alto Research Center. And the Palo Alto Research Center actually came out with tons of really cool stuff, even when Xerox was involved with it. They just used it as a research facility, though, and never really truly capitalized on any of this equipment. So Xerox PARC, really, they were responsible for inventing the laser printer, the mouse, the word processor with WYSIWYG capabilities. Now you might have to be relatively old to remember the word WYSIWYG, but it stands for what you see is what you get. WYSWYG. What you see is what you get. Graphical user interface. We're so used to this today, we don't even think about anything else as a possibility for the most part. They also invented the word processor, the graphical user interface in general, and Ethernet. So Bob Metcalfe really designed Ethernet in 73, 74. And at the time, it was an experimental thing. It was used in their labs. It wasn't until 1980 where an organization first commercialized Ethernet. And then by 82, another guy by the name of Rick Seifert actually rewrote Ethernet pretty much completely from scratch. He built it on the fundamentals that Bob Metcalfe designed and then rewrote it entirely, and he called it Ethernet 2. Now, Rich Seifert didn't do this alone when he developed this. He actually worked in a kind of consortium. So the consortium consisted of a strange group of three organizations: Digital Electronic Computing, Xerox, and Intel. Now, Xerox had the technology for Ethernet, and DEC, with Rich Seifert, really wanted to capitalize on this technology of creating a local area network that can be eventually commercialized. DEC and Xerox got together and they started working on this, except they ran into a problem, and that is, now this is in 1982, computers were not pervasive at this point. They're not like they are today. As a matter of fact, cell phones weren't even around. I don't think the Bell system had been broken up yet in the telephone company yet, if you're old enough to remember that in the early 80s. So, remember, we're very early on in IT technology at this point. So what DEC and Xerox needed was they needed somebody to make the chips for the network interface cards. And there's really only one company on earth that could handle that kind of load, and that was Intel. So they brought Intel to the table for this conversation of writing the specification for Ethernet merely because they needed somebody to make the chips to make the network interface card work. All right, so they got together and they wrote the Ethernet specification. They ratified it with the Institute of Electronic and Electrical Engineers, IEEE, as specification number 802.3. Now that number, 802.3, that sounds very familiar to a number that's actually marketed to us on packaging when we go into any big box computer electronics store, right? 802.11 is wireless Ethernet. So you can imagine who wrote the wireless Ethernet spec 2, or who ratified the wireless Ethernet specification, I should say, and that's the Institute of Electronic and Electrical Engineers, IEEE. So all of our Ethernet specifications are actually falling under the IEEE standardization body for writing this particular specification. Now, other specifications for internetworking, as we found out, are actually in a more open source model, which is the RFC model. This model of using IEEE to register and maintain the Ethernet specification results in you having to pay a license fee in order to get use of the Ethernet spec. As I understand it, it's not an overly burdensome fee. However, it's still something you have to pay, and typically only manufacturers of network interface cards want these specifications. All right, so let's continue on with this history lesson just a bit here, and then I'll quickly move on to how Ethernet actually works. So later on then, in 1989, we finally came out with a switch. So almost 16 years had passed since the advent of Ethernet before we had a switch to use in the environment. Finally in 95, 6 years after the switch came out, we came out with 100 megabit full duplex Ethernet. And then in 98, the 1 gigabit Ethernet specification was ratified. And as we go on now, we're up at 10 gigabit, 100 gigabit, and they're working on more. So we're getting faster and faster and faster throughputs through Ethernet as that technology grows. Now, the original Ethernet specification is really important to know, actually, because it used these 6 letters to describe it. CSMA CD. Carrier Sense Multiple Access with Collision Detect. And this is what Rich Seifert actually designed into Ethernet to make it Ethernet. And the way it works is like this. When we use a shared medium in Ethernet, meaning that all of the devices in our network use the same wire for communication. This is in the same way that your home telephone network may have worked. All right, you may have had extensions in your house. So you have one telephone number for your house, but you have a telephone in the kitchen, in the living room, in the bedroom, maybe even one in the bathroom, in the basement, in the garage. There's phones all over the house. And when somebody calls you, all the phones in the house ring. And the other piece is when your sister's chatting with her girlfriend on the phone and you try to pick it up to call your buddy, you can't talk because your sister's talking on the phone. Well, this, what I just described, is carrier sense multiple access. All right, you have multiple people using this telephone system in your house. Since only one person can be using the telephone at a time, when we want to find out if we can use the telephone or not, we have to pick it up and listen and see if somebody's talking. If somebody's talking, we have to either hang up or yell at our sister to get off the darn phone. Anyway, we're using the shared medium, and we have to verify that the medium is free in order for us to communicate. Ethernet works in the same way. What it's going to do is it's going to listen to the wire, and if there's no one talking on the wire, it's going to send its message out to the wire. And when it sends the message out, every single device connected to the wire receives the message. So that is carrier sense and multiple access. So each device is going to wait to hear that there's nothing being transmitted on the wires. Once it hears there's nothing being transmitted, it then sends its message, and every device connected to that wire can hear about it. This can create a problem though, because if 2 devices listen to the wire at the same time and they both send a message out, a collision occurs. Bam! And when a collision occurs, what's happening is it's actually creating a voltage spike. We measure the potential difference of electricity on a wire in volts. Well, when we're using Ethernet, we send 5 volts of electricity onto the wire to put the signal onto the wire. Well, if 2 devices put 5 volts of electricity onto a wire at the same time, what happens is the 5 volts add up and you get a 10 volt spike. Well, what happens is the network interface cards on all of our devices are designed to listen for a 10 volt spike. That way, if this collision does occur, the collision occurs, bam, the 10 volt spike happens. Every device on the network hears the 10 volt spike. When it hears the 10 volt spike, all the devices on the network back off, they stop listening, they discard any information they've received, and then the devices have to retransmit at a random interval. So now the 2 devices sending the data would wait a random interval of time and then retransmit the information, and this time hopefully there would be no collision. Now this seems kind of inefficient, where we're just kind of randomly waiting to send data onto the wire, checking the wire to see if anybody's talking, and then the first available moment we send data out onto the wire. This seems inefficient, but it's not. It's actually incredibly efficient. But what we have done long term is actually abandoned a lot of this CSMA CD.